All right. Good morning. Well, once again, whatever time of day it is for you. Um, we're going to start talking about, find my place here, molarity. So concentrations of solutions. There are lots of different ways to measure concentrations of a solution. We are going to talk about a lot of those later in the year, but the main one that I want to talk about for now is molarity. And those of you who had me last year, we talked about this just at the very end of the year, so um, you're probably still going to need a refresher here. But for those of you who had Ernst, I don't think that you got to this, so this is going to be kind of a new concept for you. But it's not difficult. Um, it's a fairly simple thing to figure out. So all you need to do is just remember one basic equation, okay? And all we're doing here is we're trying to express the concentration of a solution. Is it strong? Is it dilute? You drink Kool-Aid and you say, wow, this is really strong Kool-Aid, or you drink it and you say, wow, this is really watery. Well, in chemistry, we want numbers to express these things rather than just descriptive words. And so that's what molarity is, okay? It's one way to measure the concentration of a solution. And molarity is going to equal moles of solute over the volume of solution. Okay, now we talked last year about solute and solvent, and I just want to make sure you remember those terms. Solute is the substance being dissolved. Okay, so in the Kool-Aid example, the Kool-Aid powder is the solute. Okay, and then we also talked about solvent, and that's the thing doing the dissolving. Okay, but the solvent doesn't really come into this formula. The solute does, and then solution. Okay, and so basically, if we take the moles of the solute, the moles of the solid that's being dissolved in the liquid, usually that's what we're going to talk about when we're talking about molarity, and we divide that by the total volume of the solution in liters. That's important. It has to be in liters to be molarity. That's going to give us the concentration of the solution. And molarity is big M, usually italicized. It's not always going to be italicized, but usually. So big M stands for molarity. Okay, so here's a sample problem with this. We want to know the molarity of a solution made by dissolving 23.4 grams of sodium sulfate in enough water to form 125 milliliters of the solution. Okay, so again, molarity equals moles of the solute over liters of solution. Okay? Well, we don't know the moles of the solute yet, okay? But that's something that we can figure out pretty easily. So we've got 23.4 grams of the solute, which is sodium sulfate, Na2SO4, and we need to figure out how many moles that is. So we just use the molar mass from the periodic table. In 1 mole, there are, let's see, sodium's about 23. I'm going to approximate a little bit here. 142.1 grams. Again, if that's not specific enough for you, then go ahead and figure it out to more decimal places, but that's approximately what it is. So we take 23.4 divided by this answer, and that's going to give us about 0.165 moles of the sodium sulfate. Okay, and then we can just plug this back into the molarity equation. 0.165 moles of the solute divided by liters of solution. Now, this volume they give us, it's 125 milliliters, so we have to change that to liters. That's going to be 0.125 liters of solution. Okay, so you take the moles divided by the liters, and you're going to get a molarity of about 1.32. And the way that you usually express this is by putting just a big M, 1.32 M. Or you could also write it as 1.32 moles per liter. Either way is acceptable, okay? Because molarity is moles over liters. So either way you want to write the unit is fine. All right, next. What are the molar concentrations of each of the ions present in a 0.025 molar aqueous solution of calcium nitrate. Okay, this is kind of a tricky question because this forces us to go back to the mole thing we were talking about when something splits apart into its ions in a solution. Okay, so first of all, it would be good to know what calcium nitrate is. Calcium nitrate, calcium's a 2 plus, nitrate is a 1 minus, so that's going to be CaNO3 2. And we have a 0.025 molar solution of that. Okay, so let's just think about this in terms of moles here. Let's assume for just a minute that we have 1 liter of solution. Okay, then that means if we have 1 liter of solution, since molarity is moles over liters, and we know that we have 0.025 molar solution, and it's 1 liter, so then the number of moles is equal to the molarity here. Okay, so assuming that we have a 1 liter solution, we have 0.025 moles of the calcium nitrate. Okay, so then we just got to think about how that's going to split apart when it goes into water. Okay, so when this splits apart, there's going to be a Ca2 plus. Okay, and there's going to be 0.025 moles of that Ca2 plus ion. Okay, and then there's actually going to be 2 NO3 minuses that split apart from that, and each of those is going to be 0.025 moles. Okay, and hopefully that makes sense. Again, remember, mole is just a counting unit, so we're just counting the number of things that we have. Okay, so we have 0.025 moles of the calcium nitrate, but then we break that apart into 3 pieces, calcium 2 plus and then 2 NO3 minuses. When we break that apart into 3 pieces, we now have 3 times as much of it, if we're counting it, than we did before. Okay, so the way that that works then is that if they want to know the concentration of each of the ions, then we need to talk about the Ca2 plus and the NO3 minus, because that's what it splits apart into. Okay, so the concentration of the Ca2 plus, well, we still just have 0.025 moles of that, right? Because it only split apart into one thing. And so for every 1 calcium nitrate, we get 1 calcium 2 plus ion. So that's still going to be the same concentration as the original solution, 0.025 molar. Okay, because again, we're assuming that we're in a 1 liter solution here. So 0.025 moles divided by 1 liter gives you 0.025 molar. Okay, and then the NO3 minus here, well, that's a little different because we actually have 2 of those. Okay, and so the concentration now, or the moles of that, is going to be 0.050, which means the concentration is also 0.050 because we have 0.050 moles for every 1 liter. Okay, and so when this thing splits apart to solution, that's going to be the concentration of our ions. And again, I know it's a little weird that we start with 0.025 moles of something and we end up with a total of 0.075 moles. But it sort of makes sense if you think about it, because it breaks apart into 3 pieces. 0.075 is 3 times as much as 0.025. So we would expect to have 3 times as many pieces when we count them at the end as we did when we started. Okay? Hopefully that makes sense. If it doesn't, come talk to me. I know that's kind of a tricky concept. Alright. How many grams of Na2SO4 are required to make 0.350 liters of 0.500 molar Na2SO4? Well, now they're kind of going backwards, okay? But again, this is still with the same equation, molarity equals moles over liters. This time they're giving us the volume, and they're giving us the concentration. And we have to solve for this, but really what they want is grams. So once we find moles, then we're going to have to convert back to grams, okay? So we can plug this into what we have. We can plug it into the equation. 0.500 molar equals moles over 0.350 liters. Okay. Now to solve for moles here, we just multiply both sides by the 0.350. So the moles of Na2SO4 is going to equal, I should be able to do this in my head, 0.175. Please don't be laughing at me right now. You guys are laughing at me, I know that. But I did it in my head. I promise I didn't use a calculator just then. 0.175 moles. Excuse me. So that's the number of moles that we have, okay? Then we have to convert that back to grams. In 1 mole of Na2SO4, I just figured this out. Should just go back and look at it, but I'll recalculate it real quick. 142.1. Okay, and then we multiply that by 0.175. It's going to give us 24.9 grams. Okay, so that's how many grams of the Na2SO4 that we need in order to make a 0.5 molar solution, 350 milliliters of it, or 0.350 liters. Alright, now let's talk about dilution a little bit. When we dilute something, you probably are familiar with that term. If your Kool-Aid is too strong, then you can add some water to it, and that will dilute the solution. Okay. There are times in chemistry when we might want to do that. You actually did that on your last lab with the acid-base reaction. You diluted the hydrochloric acid. So you took some of the whatever concentration that solution was to begin with, and you actually added some water to it to make it less concentrated. Okay. Now, an important thing to remember about dilution: the moles of the solute in the concentrated solution equals the moles of solute in the dilute solution. In other words, in the acid in our lab, we had a certain number of H+ ions running around in that solution. Okay. When we added water into that solution, there are still the same number of H+ ions at the end. Okay. Now, it's less concentrated because now we have more overall solution, but we still have the same number of moles of H+ ions as we did at the beginning. Okay. And so that's actually going to help us with something in a second. That's why I'm making that point. So we can use this fact to derive an equation for dilution. So again, we know that moles of solute, let's call this concentrated, are equal to the moles of the solute in the dilute solution. Okay. Hopefully that makes sense. So here's the thing that we need to remember here, okay? Again, molarity equals moles over liters, right? Or moles over, let's just say volume for now, because we're gonna make an equation here. Moles over volume, okay? So what we have to do here is rearrange this equation a little bit, okay? Moles equals molarity times volume. If we rearrange the equation here, multiply both sides by V, that's what we get, okay? So we can actually rewrite this equation that I have up here as M concentrated times V in the concentrated solution is equal to the molarity in the dilute solution times the volume in the dilute solution. Okay? This is also known as M1V1 equals M2V2. Okay? And this is actually a very useful formula when we're talking about dilutions. So, let's do an example of that. How many milliliters of 3.0 molar H2SO4 are needed to make 450 milliliters? There's a lot of words there. So basically we've got, looks like we've got an original concentration here, and we've got a final concentration here, okay, and then a final volume. Alright, so I'm just going to label these things. This will be our M1 here. This one down here will be our M2, and this will be our V2, okay? And then what we're trying to find here is our V1. That's what we don't know. Alright, so here's our equation, M1V1 equals M2V2. Our first molarity is 3.0 molar. We multiply that times our V1, that's our unknown here, and that's going to be equal to 0.10 molar. Now here's the question, do we have to change this into liters or not? Okay, turns out because this is essentially a proportion here, we don't have to. Okay, so this equation will work even if we're using excuse me, even if we're using milliliters for our volume. Okay, because the volumes are essentially going to end up, or the molarities will end up canceling each other out when we go through this. So I can show you how the units all work. So this is what we end up with here. Okay, and so when we work this all out, we've got 3.0 molar times V1 is equal to 4.5, and the units here are molarity times milliliters. Okay, I can't really cancel anything out there because they're different units. So then I need to solve for V1, right? So I'm going to divide both sides by 3.0 molar, divide by 3.0 molar, and see how nice that works out. The units cancel out and it leaves us with milliliters. All we have to do here is take 4.5 divided by 3, and you end up getting 1.5 milliliters for the initial volume that you need to add. Okay, let me just double check my numbers here. Nope, that's not right. I tried to do math in my head. This is 45, not 4.5. Sorry about that. 45. Okay, so then when we divide the 45 by 3, we get 15. I knew that didn't look right. So 15 milliliters, it takes 15 milliliters of the 3.0 molar solution, and then you dilute it with water to 450 milliliters, and that's going to give you your 0.1 molar solution. So that's how you get it from 3.0 molar to 0.1 molar. Okay. All right, using molarities and stoichiometric calculations, I think this is a good place to stop, make part 2, because it's a good breaking point. So we'll go ahead and stop this and pick it up on part 2.